For example, the way that atoms are arranged in a material can have a significant impact on its strength and flexibility. By studying the atomic structure of materials at the nanoscale level, scientists and engineers can gain insights into how to create materials with specific properties. One approach to studying the atomic structure of materials is to use advanced imaging techniques, such as transmission electron microscopy (TEM) or atomic force microscopy (AFM). These techniques allow researchers to visualize the structure of materials at the atomic scale, providing insights into how the atoms are arranged and how they interact with each other. Another approach to understanding the relationship between structure and properties is to use computer modeling and simulation. By using computer models to simulate the behavior of materials at the atomic or molecular level, researchers can gain insights into how changes to the structure of a material can impact its properties. In addition to understanding the atomic structure of materials, another challenge in developing super-strong, highly flexible materials is ensuring that they are both durable and reliable. For example, materials that are exposed to extreme temperatures or harsh environments may degrade over time, reducing their strength and flexibility. To address this challenge, researchers are developing new techniques for testing the durability and reliability of materials. For example, accelerated aging tests can be used to simulate the effects of long-term exposure to harsh environments, allowing researchers to identify materials that are most likely to maintain their properties over time. Another challenge in developing super-strong, highly flexible materials is ensuring that they are both cost-effective and scalable. Many materials that possess desirable properties may be too expensive or difficult to produce on a large scale, making them impractical for commercial use. To address this challenge, researchers are developing new techniques for manufacturing these materials at a lower cost and in larger quantities. For example, some researchers are exploring the use of renewable materials, such as plant fibers, to create super-strong, highly flexible materials. By using renewable materials, researchers can create materials that are both cost-effective and environmentally friendly. In addition to manufacturing techniques, another approach to addressing the challenge of cost-effectiveness is to identify new applications for these materials. By identifying new markets and applications for super-strong, highly flexible materials, researchers can create demand for these materials and drive down their cost. For example, super-strong, highly flexible materials are being studied for use in a wide range of applications, from aerospace to sports equipment. By creating materials that are optimized for specific applications, researchers can create new markets for these materials and drive down their cost. Another important consideration in the development of super-strong, highly flexible materials is their impact on the environment. Many traditional materials used in industry, such as plastics and metals, have a significant environmental impact, from the extraction of raw materials to the disposal of waste products. To address this challenge, researchers are developing new materials that are both strong and flexible, as well as environmentally friendly. For example, some researchers are exploring the use of biodegradable materials, such as cellulose, to create super-strong, highly flexible materials. By using biodegradable materials, researchers can create materials that have a minimal impact on the environment. Another approach to developing environmentally friendly materials is to use materials that are abundant and readily available. For example, some researchers are exploring the use of natural materials, such as bamboo or hemp, to create super-strong, highly flexible materials.